Hey everybody, welcome back to Math 256. This is Scott. Let's get started. So we have now finished up our investigations of Chapter 1 and on to the next, which is Chapter 2, where we will be exploring systems of differential equations. We're going to start that off with Section 2.1, where we're going to be looking at modeling with systems. All right, so first off, what are we talking about? Systems of differential equations. Well, let's just think about what that means. So a system of equations, you might remember, is a collection of equations that share the same variables, and a system of differential equations is not so different. So the setup is we have several unknown functions of t. Maybe x of t, y of t, maybe more. And we can relate these variables to each other via their t derivatives. So they're all functions of t. We can take the derivative of each of them with respect to t. And so then what that could look like is, for example, something like this. Maybe we have dx dt is equal to xy minus x, something like that. And dy dt is equal to maybe y minus xy, something like that. So this is what, generally speaking, a system of differential equations looks like. All right, then what does it mean to solve the system of differential equations? It means to find each of the two dependent variables, that's x and y, each as functions of t. So solving a system that means find each of the functions of t. So in particular, you'll have as many functions as you, or you'll have as many components to the solution as you have functions in question here. Systems can be given initial conditions and specific solutions will then be sought. So until you have initial conditions, all you can get are families of solutions, just like with regular differential equations. And specific solutions will then be found. All right, so first let's talk about the way systems can enter our lives. How can systems of differential equations emerge, and then we'll discuss something of the geometry of the systems of differential equations and a little bit of the math. Most of the math and most of the geometry will be covered in later sections. This is just us getting our bearings. All right, so do systems come from? So where do systems come from? Where do these emerge? And basically, there are two main sources of systems. One, the most natural one, perhaps, is that we are actually talking about something that specifically does involve multiple variables. One, so they can arise naturally. So these are situations in which there are multiple related quantities. And some classic examples would involve, for one thing, uh, predator-prey models. And in particular, this is a classic example of a differential equation, the Volterra-Lotka equations for predator-prey models, which we'll be exploring in a project actually in this class, but which we can introduce here. They were introduced first in the 1920s and have been a very reliable example of differential equations as seen in actual nature. And here, what those look like are these. So dx dt is equal to alpha x minus beta xy. So this has a very similar look to the example we just made. And dy dt is equal to negative gamma y uh, plus delta xy, where where uh, where x represents the prey and y is the predator. And we won't go over this in a huge amount of detail right now, but essentially you can tell this just by looking at the individual components of the differential equations. So whenever you have a system and it involves a term that has the product of the two variables, that in some ways is usual, or that is somehow usually supposed to represent interactions between the two quantities. So for example, right here and right here, those represent the two situations of predator-prey interaction as experienced by each of the two categories, and in particular for the prey, interacting with the predator is bad, and it ends up subtracting from your population, hence the negative. Whereas for the predator, interacting with the prey is good and increases your population, hence the positive. And the other terms here represent essentially what would be happening to the populations in the absence of the other species. So here we have growth. That's what would happen to the prey were there no predator. Here we have decline, and that's what would be happening to the predator without any food to eat. So that's one example. And we'll, as I said, look at that in more detail in a project 3, in fact, of this course. Okay, another one is the Ir Epidemic Model. And here, what we have are three populations. So S, this corresponds to the susceptible population. So those are the people who are at risk of getting the contagion, whatever it is. So this is susceptible population. I represents the infected, like the currently infected population, and R, that represents the recovered or removed, in other words, removed from susceptibility population. So recovered / removed population. So these are people who are no longer susceptible, either because they have recovered and they are now immune, or they are, or perhaps they are deceased and no longer eligible to get the disease. So then the actual equations for these involve several parameters, just as the predator prey one does, but they come down to this: ds dt is equal to negative alpha s times I. We have di dt, which is equal to alpha si minus beta I, and then we have dr dt, which is equal to beta I. And the meanings of these various pieces, so the alpha here, so the alpha, this represents the rate of infection, or rate of transmission, I should say. So this, this essentially represents trying to model what is the likelihood that any given infected person will infect any given susceptible person. So here, for example, when we see the ds dt, these were the healthy people who were susceptible to the disease but did not yet have it. What's going to be happening to the population of these susceptible people? It will be going down in proportion to their interactions with infected people. Now, beta here represents essentially so this is the rate at which the infected people recover. So this is the rate of recovery, and in particular, 1 over beta is the length of time an infected individual is contagious. Oops, is contagious. Okay. But again, we don't have to get into the nitty-gritty of this right now. That's all matters for later when we develop more analytical tools for dealing with these things. These are just two examples. There are many, many more. Essentially, the basic framework for these examples is situations in which you have multiple categories of individual and they are all somehow interacting with each other and the interactions are causing some change in one another. All right, so this was all category number one. Category number two. So category number one was naturally making a system because we have multiple related quantities. Situation number two, the second place where systems can arise is actually through an artificial process in which we can convert higher order differential equations into systems. So number two, we can convert higher order equations into systems. The process. So here's the fundamental idea. So we have a single higher order equation. So this is maybe just in one, so it's an equation that involves one variable and its derivatives, it's got its second derivative, it's got maybe its third derivative, and so on. So here's the process. So first off, the setup. We have a single high order, namely higher than 1, high order differential equation. So for example, let's just say we have something along the lines of x double prime. We'll just start with something something of order 2 plus 3x prime plus 2x is equal to 0. With initial conditions, let's say of x of 0 equals 1 and x prime of 0 equals 2. Something like that. So if we have this higher order differential equation like this, and some initial conditions we will typically want, then we can try to create a system by making essentially each of our new variables in our system one of the derivatives of the original variable. So we create a system of equations by naming the successive derivatives up to 1 less than the order of the differential equation by naming the successive derivatives as new functions. So in particular here, we can just name the new functions. We can call them x1, x2, x3, for example. We can give them some other new name, like we can call them like a of t, b of t, c of t, something like that. We have several options here, but I think I'm just going to go with x1, x2, x3, and essentially x1 is just going to equal the original x. So this is the original x. X2 is going to equal x prime. And then what that means is that x2 is equal to x1 prime. So that gives us one of our differential equations. And then the other fact here is that if the derivative of this is going to be the second derivative, then that means x2 prime equals x prime prime, which then is which we can then relate to the original equation. Which we can relate to the original equation. And in particular, what we would have is then x double prime plus 3x prime plus 2x equals 0. This would be, which then we can translate now into our new system of variables. So x double prime, also known as x2 prime, plus 3x prime. What's x prime? X prime is the same thing as just x2. And then plus 2x, what's x? In our new language, that's x1, which we would then just solve for the derivative, since we're trying to make a differential equation. So that means x2 prime is equal to, and now we'd want to write the variables in their sort of canonical order, which would be x1 before x2, so that'd be minus 2x1 minus 3x2. Okay, and that would represent the second of our two equations. And so then our system would look like this. So we're trying to make a system of differential equations. So those are equations that have the first derivatives of the two variables that we're talking about. So what's x1 prime? Well, as we saw up here, that's equal to x2. So now, what's x2 prime? That's equal to negative 2x1 minus 3x2. And then we also have the initial conditions, which were originally formulated in terms of x and x prime, but now we can formulate them in terms of x1 and x2. So x1 of 0 is equal to 1, and x2 of 0 is equal to 2. Let's try another example of this before we move on. What if we had something like this? D squared x, which remember is over dt squared. Remember, this is the Leibniz notation for second derivative. Plus dx dt plus 3x is equal to cosine t. And let's say that x of 0 is equal to 4. And let's say x prime of 0 is equal to negative 2. All right. Well, once again, we have actually a very stereotyped process here. We're just going to make x1 equal to x prime. sorry, equal to just x, I mean. And then we're going to make, so then that means that x1 prime, which is the same as just x prime, that's going to be what we're going to call x2. And then for the original differential equation there, we've got, I'm just going to reformulate it in terms of primes because it's a little bit more straightforward. X double prime plus x prime plus 3x equals cosine t. Now we can just try to put this in terms of our new friends x1 and x2. So then I guess x2 prime is equal to x double prime. Okay, so this is going to be x2 prime plus x2 plus 3x1 equals cosine t. And notice, okay, so be it. There is there's still a t in here, which there wasn't before. So this is not what is called an autonomous system, where the t's are absent, but it's still a fine system in its own right. And then I would just solve this for the x2 prime to make the differential equation. So what is that going to equal? That's going to equal, it looks like we're going to have negative 3x1 minus x2 plus cosine t. And then that means our system is then going to consist of x1 prime, x2 prime. That's how you make a system of first order differential equations. It's just something prime equals this, something else prime equals that. And the x1 prime, that is equal to just x2. x2 prime, that's what we just found. That's equal to negative 3x1 minus x2 plus cosine t. Then and then we have, of course, our initial conditions, which are that x1 of 0 is equal to whatever it equals. What did we say? So x1 is the same as x, so x1 of 0 equals 4, and x2 of 0 is equal to negative 2. Okay, but now the real question is, why? Why would we want to go through this process? This process is not the hardest one in all of math, but we ought to have a good reason for doing it if we're going to be learning about it. So why do this? The answer is that without doing something like this, there is no way to actually either graphically or numerically represent higher order differential equations. We can't directly represent higher order ODEs graphically or numerically without going through this process. Now, systems, on the other hand, can be represented in that manner. So the way we can represent systems is through what is called the phase plane. Phase plane. So this is actually a graphical representation of the dependent variables with respect to one another. So the phase plane, this is a representation of y versus x. And then we can make what is called a direction field. And this corresponds to a slope field if we're just talking about a single ordinary differential equation. But in the case of a system, this consists of a bunch of vectors which indicate direction for solutions. So a direction field, this gives vectors that point the directions of solution curves on the phase plane. And then trajectories or solution curves. These represent the curves where y is plotted against x, for example. So these represent the curves where y again is plotted against x. So these are not always the easiest things to understand, but they are an important tool in doing all sorts of other pieces of analysis. And then the part that is more useful often are the time plots. And these are x and y each plotted with respect to time. So x and y are plotted, and actually I should say x and y are plotted separately with respect to time, rather than being plotted against one another. So with respect to t, instead of with respect to one another. Okay, so these are the ways that we can actually represent the graphical representation of systems, which is not an option that is available to us for mere higher order equations. So that's one of the main reasons why we would produce this, is because we often need a graphical or an approximate solution, and that requires a conversion to a system. All right, so let's go ahead and switch over now to some of the graphical side of things and see what these things generally look like. All right, here we are at the Google search results for Bluffton differential equations. If you just follow the first one on there, we are at our usual place. this. Somebody else has been up to some curving. Some curve sketching. It looks like, and I'm just going to take this now, and let's look at the options that are available to us. All right, so you'll notice that there is no option for a higher order differential equation. However, there is an option for a system of differential equations. And here we can put in the system that we created out of that second order differential equation, which was, if we'll recall, so the system that we created it was x1 prime equals x2, and x2 prime was equal to negative 2x1 minus 3x2. So we'll just put that in. Remember, we have to respect the variables as the Bluffton understands them. So we're just going to use x and y for x1 and x2. That means this is going to be equal to y. And this one is going to be equal to negative 2x minus 3y. Okay, so this is what our direction field looks like. So notice, as opposed to a slope field, where we just see little line segments, these ones are little vectors, and they point in the direction of the trajectories that we would see when we plot y versus x. So now, if we put in the initial conditions, so the initial y condition here was, or sorry, x condition was 4. No, wrong one. 1 and 2. 1 and 2 was what they were. So sorry, I just lost my view of the thing here. Just 1 second. Okay. So so then we will just put those in here. So this was 1 and 2. All right, so that's what our solution curve looks like. It just is swooping down like this, and this is y, this is x. So we are looking at the trajectory of y versus x. Now, y itself does not actually have that great a meaning for us because y was an artificial variable that we created. X is the important one. So if we wanted to actually, think about what the solution to our differential equation looks like, we would have to click down here and have a look at, for example, the time plot. So, so this is a time plot. It is showing x and y separately with respect to time, and you'll notice here that we've got. Zoom in. You'll notice that what we've got here is there we go, that's better. We've got the X in red, we've got the Y in blue. Now the Y, we don't actually really care about so much. We invented X2. X1 though represents the actual function that would be the solution to this differential equation. So here you'll notice it swoops up and then it kind of levels off at 0. So this would be the actual solution to the original differential equation. And over here we have a table of values that we can generate by means of the Runge-Kutta method that was just now employed to sketch this solution curve. So that is what these generally look like. We'll get into the nitty-gritty of the graphing of these and trying to understand what the graphs can tell us about the differential equations as we explore in greater depth in the next couple of sections. But for now, we just wanted a very basic overview, and that's what we've got. So join me next time for a continuation of this in the next episode of Math 256. Until then, bye.